So in all of those previous questions that we worked on, where we converted from a gram amount of a substance to the mole amount of the substance, and then used stoichiometry to convert to a different mole amount of a different substance, we assumed that those reactions went on completely. That the reaction went completely. That all of the mass of the reactant reacted to produce a product. That's not how things work out in real life. If you combine two things together to create one product, typically one of those substances of reactants will run out first. Um, so this brings us to the topic of limiting reactants. So the availability of the reactants, depending on how much stuff you put into, your reaction vessel, one of them will run out first. And whatever runs out first limits the amount of product that you can form. So we have some definitions here. There's a limiting reactant. So this is the reactant that's used up first, and it limits the amount of product that you make at the end because it's what runs out first. And then if, let's say, there's two different reactants, like if there's like an A plus B gives us a C. So let's say A is our limiting reactant that runs out first, and then B, that substance, is our excess reactant. And that reactant is present in a larger quantity based upon the coefficients, and there's some of it left over after the reaction finishes. So we've kind of already looked at the concepts of limiting and excess reactants before at the beginning of the semester when we talked about baking a cake. So I'll just kind of bring that example back up because I think we've all cooked in the kitchen in some capacity and run out of ingredients. So I think that's a concept that students can grasp pretty easily, and it directly relates to our concepts of limiting reactants. So let's pretend we're making this cake. So Martha Stewart's pound cake recipe calls for 2 sticks of butter, 2 cups of flour, 1 cup of sugar, and 4 eggs. So this will make a cake. So, we could, write a chemical equation for this. So essentially this is 2 sticks of butter plus 2 cups of flour plus a cup of sugar and 4 eggs. So those are all our reactants, and it produces a cake or one cake. So this is technically a combination reaction where we're combining these 4 ingredients and we get one product at the end, a cake. And then you can see here are our coefficients: 2 sticks of butter, 2 cups of flour, 1 cup of sugar, 4 eggs. Those are our coefficients in this chemical equation to give us this product of one cake. That's also a coefficient. All right. And we did this question before, where like you're hosting a party, you need to figure out what's the maximum number of cakes you can make using this recipe when your kitchen is stocked with these things. You have 24 sticks of butter, 30 cups of flour, 11 cups of sugar, and 4 dozen eggs. What's the maximum number of cakes you can make? So with this information, I can ask you a bunch of different questions. So I can ask, okay, what ingredient will run out first? If you're using this recipe and this is your the amount of reactants that you have, what runs out first? This is your limiting reactant. And then, or another way I can ask it is, okay, how many cakes can you make? Like, what's the maximum number of cakes you can make? So to figure that out, you need to take whatever the limiting reactant is, whatever runs out first, and use the coefficients to figure out, okay, how many cake products can you make? So the important thing here is that you use whatever runs out first to calculate how that is what will determine how many cakes or how much product you make. Because if you run out of eggs, then that's going to determine how many cakes you can make if that's your least amount of substance or of reactants. And then finally, I can ask, okay, what's left over after you make all of the maximum possible cakes? What ingredients are left over? Those are your excess reactants. So see how baking a cake relates exactly to our concepts of limiting and excess reactants. So let's actually answer those questions. All right, so I gave myself some more room here. So our questions here are, so this is what you're stocked with. I'm going to copy my reaction down here. I'll just move it. Okay, so there's my reaction. So I have some questions. What ingredient runs out first? How many cakes can you make, and what's left over? So our kitchen is stocked with 24 sticks of butter, 30 cups of flour, 11 cups of sugar, and 4 dozen eggs. So note how in the reaction it just says, it needs 4 eggs. So I'm going to just quick convert 4 dozen eggs to just, single eggs. So that's 48 eggs. So 48 eggs. All right. So that's what my kitchen is stocked with. So usually how I approach limiting reactants like this is I calculate what is the max number of product we can make. So in this case, cakes, max product or cake can you make with each of these ingredients? What's the maximum number you can make? So we're assuming, like here with 24 sticks of butter. So with 24 sticks of butter, I see that the reaction requires 2 sticks of butter to make a cake. So I know, okay, that cake requires 2 sticks of butter, so I can only make 12 cakes with the amount of butter I have. So you're essentially assuming that you're not limited by the other substances. So I'll go through each of these and determine, okay, what's the maximum number I can make, assuming that we don't run out of the other things. So once you get the max numbers for all 4 ingredients, you can look at, okay, what is the lowest amount? What will run out first? What is the lowest amount of cakes you can make? Because that is what determines, that's your limiting reactant. That's what determines the amount of cakes at the end you can make. So, I mean, I could actually do the stoichiometry here, right? So 2 sticks of butter makes 1 cake. So 2 sticks of butter makes 1 cake. So I can make 12 cakes with those sticks of butter. And then for flour, so 2 cups of flour can give us 1 cake. So 2 cups of flour, 2 flour, 1 cake, right? So this is the same dimensional analysis we've done before. That can make 15 cakes, assuming that we don't run out of anything else. 11 cups of sugar, so it's a 1-to-1 ratio. So 11 cups of sugar can make 11 cakes. And then finally, 48 eggs. So 4 eggs will make 1 cake. So 4 eggs, 1 cake. So I can make 12 cakes without amount of eggs. So those are the maximum. That's the maximum amount of cakes you can make from these different ingredients. So you see here that with cups of flour, that has the lowest amount of cake. So sugar will run out first. Once I make that 11th cake, I will have no more sugar and I cannot make any more cakes because sugar is required in this chemical reaction. So sugar is our limiting. So sugar, what was the first question? Which ingredient runs out first? So sugar is our limiting reactant because it runs out first. After making that 11th cake, we'll have no more sugar and we'll have stuff left over. Limiting reactant. And then it says this other question, so the answer is sugar. How many cakes can you make? So it's after the 11th, after the 11th cake, you'll make your 11th cake and you can't make any more. So 11 is the amount of cakes you can make. So remember how I said it's the limiting reactant is what determines how much product you can make. So how many cakes you can make? It's 11, and sugar is what determined that. And then finally, what is left over? So butter, flour, and eggs will all be left over. We can calculate how much will be left over. So we can determine, okay, how much ingredients to make 11 cakes, because we've made 11 cakes. So we will consume butter that made 11 cakes. So I can think, okay, to make 11 cakes, I will need 22 sticks of butter. In order to make 11 cakes, what you need 2 cups of flour. So 2 times 11 cakes is we need 22 cups of flour. To make 11 cakes, you need 11 cups of sugar. And to make 11 cakes, you need 11 times 4. You need 44 eggs. Sugar, flour, and butter. So we can calculate what is excess, what's left over at the end after you finish all of your baking. So if you take the amount that we used and what we started with, you just subtract those two things, and that will tell you what's left over. So we started with 24 sticks of butter, but we only used 22 in order to make 11 cakes. So we should have 2 sticks of butter left over. If we look at flour, we used 22 cups of flour. We started with 30, so we should have 8 cups of flour left over. Sugar, so see how we needed 11 cups of sugar. We started with 11 cups of sugar, so that actually runs out. So we have no sugar left over. And that makes sense because it's our limiting reactant. And finally, 48 eggs. So we used 44. We had 48, so we should have 4 eggs left over. So that is our last answer. What is left over? Butter, flour, and eggs are our excess reactants, and then we calculated how much is left over. So this is essentially, I can ask you questions, but with actual, real chemical reactions, not baking a cake, but it's still this same process where you have to figure out what runs out first. And the easiest way to do that is to calculate, okay, how much product can you make from that amount of reactant, and then choose the smallest one. Okay, so let's actually do a chemical reaction. So let's look at this combination reaction. Is it balanced? Yes, it is balanced. So it says, suppose you have 12 grams of carbon and you react it with 64 grams of oxygen. How much CO2 is produced in grams? So it's telling us we're starting with 12 grams of carbon and 64 grams of oxygen, and we want to know, excuse me, how much CO2 you produce at the end. So just like in our previous example where I calculated, okay, what is the max number of cakes I can make? I'm going to do the same thing here. I'm going to figure out, okay, how much will 12 grams of CO2 make? And then I'll also calculate how much grams of, or how much will 64 grams of oxygen, how much CO2 will 64 grams of oxygen make? And then you just pick the lowest one. So that is my strategy here, because they're just telling us, okay, you just combine this much carbon, this much oxygen. In that question, it doesn't tell you what the limiting reactant is. You have to figure that out yourself and figure out, okay, which one will run out first. So my strategy here is to determine mass of CO2 that can be produced by each reactant. And then you just pick whatever is the smallest number. Pick smallest number. And that would be our limit. That's indicating our limiting reactant, that one will run out first. Limiting reactant. So that's my strategy. So essentially, with this question and limiting reactant questions, it's no different than like those 3 examples we did before. It's just now, since you're given masses of 2 different reactants, you just have to do stoichiometry twice, and then you just pick the lowest one. Do I give more space? Yes. Okay, great. I give you more space. So essentially, I'm going to be asking or trying to figure out, okay, 12 grams of carbon will produce how many grams of CO2? And then I'll also calculate, okay, 64 grams of O2 will produce how many grams of CO2 using the coefficients in the balanced equation. And so this is no different than the other ones that we did. So we'll either start with grams of carbon. We need to go to moles of carbon, to moles of CO2, and then grams of CO2. And then we need to do this again for oxygen. So start with grams of oxygen, go to moles of oxygen, then to moles of CO2, and then grams of CO2. We're essentially just doing two stoichiometry questions with each of the numbers given. So let me give you molar masses. So the molar mass of carbon is 12.01 grams per mole. The molar mass of oxygen, diatomic oxygen, because there's two oxygen atoms, is 32.00 grams per mole. And then the molar mass of CO2 is 44.01 grams per mole. All right. So we'll need all those numbers to convert between grams and moles of substances. All right. But to go from moles of carbon to moles of CO2, we use the coefficients in our balanced equation. We use stoichiometry. All right. So I'm going to start with the carbon one first. So 12 grams of carbon. I need to go to moles of carbon. So 12.01 grams of carbon, 1 mole of carbon. Now I use stoichiometry. So I see that it's just a 1-to-1 ratio. That's easy. So just 1 mole of carbon will make 1 mole of CO2. And then I need to go to grams of CO2. So molar mass, 1 mole of CO2 gives us 44.01 grams of CO2. And that will equal some number. I'll do the next one before I calculate it. So let's do the second reactant that's given, 64 grams of oxygen, and you'll see that this will look exactly the same. It's just we use the numbers for oxygen instead. So I need to convert from grams of oxygen to moles of oxygen. So I use the molar mass, so 32.0 grams of oxygen is 1 mole of oxygen gas. So now let's look at stoichiometry. So 1 mole of oxygen will make 1 mole of CO2, right? All of these are just one implied ones. So again, it's just a 1-to-1 ratio, so that's kind of easy. 1 mole of oxygen gives us 1 mole of CO2 using those coefficients. And then what do we need to do? Convert to grams of CO2. So 1 mole of CO2 is 44.01 grams CO2. All right, so we have our two, we essentially did stoichiometry twice. So I'm going to stick that into my calculator. So the two numbers here are 44 grams of CO2 in the first line. I won't circle that yet. And then starting with 64 grams of oxygen, you can make 88 grams of CO2. So again, like when we made our 11th cake and our sugar ran out, and so we couldn't make any more cakes, our answer here is 44 grams of CO2. Because once we make our 44th gram of CO2, we will have no more carbon left over. There'll be extra oxygen left over, but there's no carbon around, so the reaction cannot proceed. We can't make any more cakes. So our answer here is 44 grams of CO2 because carbon is our limiting reactant. All right. So again, limiting reactant questions are no different from just straight conversion questions. Those 3 examples we did previously. The only difference is that you need to calculate how much product you make with each of your different reactants and just determine which one runs out first. So the last topic that I want to talk about in chemical quantities in this lecture is percent yield. So as chemists, we calculate percent yield in the laboratory because we don't often, if we did this chemical reaction, this combination to produce CO2, and we did this reaction, carbon ran out first, sometimes we won't actually get 44 grams of CO2, the amount of product that we calculated. Sometimes we don't get that theoretical amount. Everything that we're calculating is theoretical amounts. We're assuming that everything went perfectly. We converted all of the reactants to products and we didn't lose anything. That we're assuming that the reaction is complete with the reactants. But if we think about to like our cake example, what if, and how we calculated that you can make a theoretical amount of 11 cakes. But like, let's say, for your party, let's say you burn one of your cakes and you only actually make 10. Your 11th one burnt. So if you only actually got 10 cakes at the end and you lost one of your cakes, that can give you a percent yield, essentially like a grade for or a percentage of the cakes that you actually made. Or let's say you drop a dozen eggs on the floor and you lose a dozen eggs, and now your eggs are your limiting reactant. So we're not perfect chefs. So if any of these scenarios occur where you burn something or you break something, you won't get that maximum number of cakes that we calculated. That's your theoretical yield. That 11 cakes number that we calculated, that's your theoretical yield. Because we're assuming everything went complete. But again, we're not perfect chefs. Sometimes we don't get the maximum amount. And so that's how we can calculate percent yield and compare what we actually got to what we theoretically could have made. And again, I talk about cakes, but the same applies to chemical reactions. Because we're not perfect chemists, when we're in lab, we might not actually produce the maximum number of moles of product that we initially calculated. So percent yield is an experimental number that we calculate in lab. So percent yield, here's the equation for it, where you need to calculate your theoretical yield. So it's the amount of product expected from the complete reaction of your reactants. Essentially, it means that we've converted your 100% of your reactants. And remember, typically this is determined by your limiting reactant. So all those numbers that we calculate previously, those were our theoretical yields. So here in this question, our theoretical yield will be 44 grams of CO2. We're always limited by our limiting reactant. 88 that is not our theoretical yield, it's 44 grams of CO2. And then your actual yield, this is the amount of product that you actually made during your experiment. So the equation for percent yield, just think of it as like a grade, that the maximum amount of yield you can make, that's your bottom, that's your numerator, that's your theoretical yield. And what you actually got, that's like your grade, the amount of points you scored, and you put that in your numerator, and it's probably going to be less than 1, and then you multiply by 100 to get your percentage. All right. So yeah, just think of it as like a grade. And then, so let's actually do an example here. So let's think back to this combination reaction of CO2. So let's remember the mass of CO2 that we produced from the limiting reactant in this example. Remember, we said that our 12 grams of carbon was our limiting reactant. So 12 grams of carbon made 44 grams of CO2. So this is our theoretical yield. So let's pretend, what if we did this reaction in lab and we only produced 39 grams of CO2? What is the percent yield? So percent yield is theoretical. Actual over theoretical. Actual over theoretical times 100. So the actual yield was 39, so you just kind of have to read that in the question. We only produced 39 grams in lab, so 39 grams of CO2. The theoretical amount of CO2 that we got from doing reaction stoichiometry and the limiting reactant is 44 grams of CO2, times 100, and that is something 89% yield. 2 sig figs, because both of these numbers only have 2 sig figs. All right, so that's a B+. That's a pretty good yield, 89%. So the maximum amount of CO2 we can produce from that reaction, according to stoichiometry, was 44 grams, but we only produced 39, or that's how much we got during the experiment. And so that's how we calculate percent yield experimentally. And so in this case, it was 89% yield. All right, so let's do one last question to kind of round this out and kind of combine all those skills that we've just learned using reaction stoichiometry and all that, and percent yields and limiting reactants. So without proper ventilation and limited oxygen, the reaction of carbon and oxygen produces carbon monoxide. So this is another combination reaction between carbon and oxygen, but this time we make carbon monoxide. So here's the balanced equation. Remember, all of this stoichiometry involves balanced equations. So in this question, it says, what is the percent yield if 40.0 grams of CO is produced when 30.0 grams of oxygen is used up? All right, so in this question, we're assuming that there's an excess amount of carbon because it doesn't say anything. So we're assuming that all of the 30.0 grams of oxygen is used up. So this is going to be our theoretical, this is the number we will use to get our theoretical yield. So, because in this question it says, what is the percent yield if 40 grams of CO is produced? So this number, 40 grams of CO, this is our actual yield. And remember, percent yield is actual over theoretical times 100. So we have our actual yield. We just need to calculate our theoretical yield. So we're going to use this 30 grams of oxygen to do that. So let's get some molar masses real quick. So the molar mass of oxygen is 32.00 grams per mole. And the molar mass of CO is 28. Yeah, 28.01 grams per mole. So again, these are all the same skills we used previously with reaction stoichiometry. So let's figure out how many moles of CO are produced from 30 grams of oxygen. So we're just going to convert 30 grams of oxygen to amount in carbon monoxide. So 30 grams of oxygen, molar mass to convert it to moles, so I can use stoichiometry. 1 mole of oxygen times, all right, so now I'm in the unit of moles of oxygen. So if you see here in our balanced equation, 1 mole of oxygen is required to make 2 moles of CO gas. So 1 mole of oxygen on bottom, 2 moles CO up top. But I want to get to grams of CO, so that would be, use the molar mass of carbon monoxide, so 1 mole of CO weighs 28.01 grams CO. All right, and then you just stick that into your calculator and you get 52.52 grams of CO. So this is our theoretical yield. We're assuming all 30 grams of this oxygen is converted to CO, just like in all the previous questions that we've been doing. So that's our theoretical yield. But this question is asking for percent yield. So percent yield is actual yield over theoretical times 100. So in this case, it is 40.0 grams of CO over our theoretical yield, which we just calculated is 52.52 grams of CO times 100. This answer should have 3 sig figs because 40.0 has 3 sig figs. And so my answer here is 76.2% yield for this reaction. All right, so this percent yield question really just summarizes all of the skills that we've learned in this lecture, looking at reaction stoichiometry, understanding how to use the coefficients in a balanced chemical reaction. You need to be in moles. Moles is your ticket to use those coefficients. And then we looked at limiting reactants, how to determine that, and percent yield.